Hello, good evening everyone. Myself P.S. Pandey, faculty of GIC campus. Today I discuss the DC circuit. In DC circuit, we first discuss active element or active source, passive element, then we discuss this unidirectional elements and bidirectional elements, and third is Kirchhoff's law, and fourth is ideal source and practical source, and fifth we discuss different types of source. So first of all we discuss what is active source and what is passive. So what do you mean by active source? The active source is a source of element that deliver a energy. There are two types of source. One is current source and another is voltage. The source that delivers the energy is called active source. So what do you mean by passive source? The passive source or passive element that absorb or release the energy is called a passive element. There are three types of passive element. One is inductor, second is capacitor, and third is resistor. Since inductor and capacitor store energy in the form of magnetic field and electric field, everyone know. But resistor dissipate energy in the form of heat. Then there are three types of elements in passive. One is inductor, second is capacitor, and third is resistor. So second we discuss what do you mean by unidirectional element, and second is bidirectional. Unidirectional element are those elements that allow the flow of current in only a one direction. It means the flow of current possible in only one direction. Both directions flow of current is not possible. But in a bidirectional element, the flow of current possible in a both directions. Example of unidirectional element is diode. In a diode, only flow of current is possible in a one direction. Second example of unidirectional element is transistor. Transistor also allow flow of current only in a one direction. But resistor, inductor, and capacitor are a bidirectional element that allow the flow of current in both directions. And we know what is a Kirchhoff's law. There are two types of Kirchhoff's law, everyone know. One is Kirchhoff's voltage law and third is Kirchhoff's current law. Then what is the statement of Kirchhoff's voltage law? Now what are the statement of Kirchhoff's current law? First we discuss Kirchhoff's voltage law. Kirchhoff's voltage law, KVL. KVL means Kirchhoff's voltage law. KVL state that, or Kirchhoff's voltage law state that algebraic sum of voltage in a closed loop is equals to, suppose one circuit, this circuit here, E is the voltage source, here one resistance R1, here second resistance R2, and third resistance R. Current flow through this circuit is I, so voltage V1 across R1 is V1, across R2 is across R2 is V2, across R3 is V. According to Kirchhoff's voltage law, the algebraic sum of voltage equals to this represent summation or algebraic sum. So here V equals to V1 plus V2 plus, so V equals to V1 minus V2 minus V equals to, these are the statement of Kirchhoff's law. It means total summations of voltage is also equals to, second is Kirchhoff's current law, KCL. KCL means Kirchhoff's current law. What are the statement of Kirchhoff's current law? The total current entering at any node is equals to total current leaving at any or any junction. Suppose A is my junction. There are 4 incoming current, I1, I2, I3 and I4. Similarly, 4 outgoing current, I5, I6, I7, I. So according to KCL, total current enter at any junction or any node or any node is equals to total current leaving at that node or here 4 current entering at a junction or at a node, I1, I2, I3 and I4 is the 4 current that enter at node A. So I1 plus I2 plus I3 plus I4 and 4 current leaving from node A or junction A. I5, I6, I7 and I8 are 4 current that leaving from node A or junction. So I5, I6, I7 and I8. These are 4 current that leaving from node A or junction. So I1 plus I2 plus I3 plus I4 equals to I5 minus I5 minus I6 minus I7 minus I8. So total I or summation of I equals to 0. The algebraic sum of current at any node or any junction equals to 0. These are the statement of Kirchhoff's current law. After Kirchhoff's law, we discussed energy. Here discuss source. We discuss source. There are two types of source. One is ideal and second is practical. One is ideal and second is practical. First, ideal voltage. Here also a practical. Second, ideal current. And practical current source. So first we discuss ideal voltage. Ideal voltage. What do you mean by ideal voltage source? When we represent a voltage source in a circuit, the ideal voltage source look like when voltage connected in series with resistance called voltage source. When source is ideal, then this R equals to, it means this R is a internal resistance of this voltage. R is internal resistance of voltage in many examinations. Questions asks what is the internal resistance of ideal voltage source. The resistance of ideal voltage source is 0. It means this is short circuit. When we draw a graph between voltage and time For ideal voltage source, then graph is always a right. But in case of practical source, this internal resistance is present with this voltage source. These are not equals to, when internal resistance is not equals to 0, in case of practical source, then there are grouping observed in voltage with a time. These are ideal and these are practical. The difference between these two are due to R. Since internal resistance is present in practical source, so graph is grouping in. When we draw a load resistance RL with this circuit and close this circuit, then total current I equals to P upon RL plus R in case of practical voltage but in case of ideal voltage source, internal resistance is 0, so only load resistance RL is connected with this. Here I current is I equals to P upon R. These are the relations between current, voltage and load resistance in case of ideal voltage but these are the relations between current, voltage and load resistance in case of ideal voltage source. Similarly, in case of current source, in current source, this current source is parallel with this internal resistance RL. In case of practical source, this current source connected in parallel with this resistance R. This R is a internal resistance of this current source. R is a internal resistance of this current when this current source is ideal, then this resistance is infinite. What do you mean by infinite? Infinite means this path is work as a open circuit. This path is work as a open circuit when R is infinite. So in case of ideal case, ideal current case of ideal current source, we represent this current source with this load resistance R. Finally, these are the voltage across a RL. So V equals to I into R in case of ideal voltage source. But when source is practical, this internal resistance is not equals to 0. This R not equals to this R not equals to when this internal resistance is not equals to 0, then this current source I in parallel with two resistance. One is internal resistance the second is load. This current source is parallel with two resistance. One is R and second is RL. R is internal resistance of this current source and RL is load. So the current through current through R is I1 and current through RL is IL. So the current through I1 is I into RL divided by RL plus R. Similarly, current through R. Current through R. Similarly, current through RL is IL I into R upon RL plus R. These are the current flow through a resistance R. This R is a internal resistance and this current IL is current flow through RL and this RL is a load resistance. When we know the current flow through R, then we easily find voltage across a R. So V equals to I1 into R. So V voltage across R equals to I RL into R upon RL plus these are the relations between voltage, current and resistance when current flow through a R in case of practical voltage source. Similarly, voltage develop or voltage across load resistance RL is VL I into I1 V into I into RL. So VL equals to, in place of IL we put IL into R into RL upon RL plus R. These are the relations between voltage, current and resistance when current flow through a load resistance IL. When current flow through a load resistance RL. When graph is drawn in case of practical and ideal, then graph is look like this. Graph is look like here current I, here time t, here. But due to presence of this internal resistance R, we observe some drooping, and this drooping is due to internal resistance R, case of practical voltage source. When drooping comes, then there is some losses, and these are present also some losses. So after discussing ideal voltage source, practical voltage source, we discuss different types of here we write source, here we write voltage source, here we write current, here we write voltage source, and second is current source. There are types of four types of source. One is voltage controlled, voltage voltage source. Second is current control, voltage source. Similarly, current side, current control, current source. Second is voltage control, current, it means ECES. ECE, VCVS means voltage control voltage source, and CCVS means current control voltage source. Similarly, current control current source is CCCS and VC as voltage control current source. So there are four types of source. One is voltage control voltage source, second is current control voltage source, third is current control current source, fourth is voltage control current source. After discussing current source, we discuss voltage divider rule and current divider. What do you mean by voltage divider and what is current divider? First, we discuss voltage divider rule and current divider rule. We discuss combination of element. There are three types of passive element. One is resistor, second is capacitor, and third is inductor. So first of all, we discuss resistor, and in resistor we discuss combination of resistor. So three types of combination. One is series combinations, second is parallel combinations, and third is series parallel combination. So first we discuss series combination. In series combination, resistance are connected in a series. Suppose here three resistance and three resistance are connected in a series. In resistance, there are two terminals, suppose A and A1. In R1, in R2, two terminals B and B1 or B dash. Third resistor is also two terminals C and C. When this resistor R1 is connected in series, then terminal A dash is connected with B and terminal B dash connected with C, and this connections is called series connections, because terminal, since each resistor has two terminals, and here resistor R1 has two terminals A and A dash, R2 has B and B dash, and R3 has C and C. The resistor R1 terminal A1 connected with B, resistor R2 terminal B dash connected C. So this connections is called series connections, and when these connections, series connections connected with voltage source, and this circuit is closed, then current start to. In series connections, the similar current is flow through each resistor. Here three resistor R1, R2 and R3, and each resistor similar current is passed. So the voltage developed across R1 is V1, across R2 is V2, across R3 is . These are the voltage across R1, across R2, across R3, when this resistor R1, R2, R3 are connected in series and connected with voltage source, then current I start to flow through this resistor. So this current I equals to V upon R1 plus R2 plus R. Because in a series combination, R equivalent is equals to R1 plus R2 plus R. So current I flow through the resistor R1, R2, R3 when resistors are connected in series equals to V upon R1 plus R2 plus R3. So V1 equals to I into R1 because current is same. V2 equals to I into R2 and V3 is equal to I into R3. We write like this. V1 is the voltage across R1, V2 is the voltage across R2 and V3 is the voltage across R. In place of I, we put V upon R1, R2, R here, R1, V2 equals to V upon R1 plus R2 plus R3 here, R2. V3 is equal to V upon R1 plus R2 plus R3 to R3. These are the voltage and resistance relation in series combinations. In series combination, these are also we discuss voltage divider rule. Voltage division rule. Why we discuss in series combinations only a voltage division rule, not a parallel division? Because in a parallel combinations, voltages are similar in a parallel. Voltages are same across each resistor in a parallel, but in a series voltages are divided in different parts. So we only discuss voltage division rules in series connections, not a parallel connection. Suppose there are three resistors R1, R2 and R3. These resistors are connected in series and also connected a DC voltage source. Current I start. So then V1 is voltage across R1, V2 is voltage across R2, V3 is across R3. So V1 equals to V upon V upon suppose this resistor not present, only two resistors are present. So V upon R2 upon R1 plus R2. Similarly, V2 equals to V into R1 upon R1 plus R2. These are the total voltage. V1 and V2 are voltage are divided. So this is called voltage division rule. Total voltage V is divided into two parts, V1 and V2, because two resistors are connected in series. when this voltage V1 and total voltage V divided into V1 and V2, then the voltage V1 is equals to total voltage V into R2 divided by R1 plus R2, and voltage V2 equals to V into R1 divided by R1 plus R. These are the voltage division rules. Second is current combination. Second is parallel combinations. Suppose three resistor R1, R2 and R3. Two terminals A and A dash, E and B dash, and there are three resistor R1, R2, R3 has two terminals A and A dash for R1, B and B dash for R2, and C dash for R3. Suppose there are two nodes N and M. This A connected with this M, this A dash, B dash, C dash connected with, and when this parallel combinations is connected with this voltage source, then same voltage is appear or observe across the resistor R1, R2 and R. These are the current flow through a voltage source. So current through R1 is I1, current through I2 is I2, R2 is I2, current through R3 is I. Since voltage is same in parallel combination, so I1 is equals to P upon R1, I2 equals to P upon R2, and I3 equals to P upon R. According to KCL, total incoming current is equals to total out outgoing current. Here incoming current is I and outgoing current is I1 plus R2, I2 plus I. So in parallel combinations, I equals to P upon R1, we write P upon R1, P upon R2, P upon R. We write here also I equals to V upon R equivalent. So V R equivalent equals to V upon R equivalent equals to V upon R1 plus V upon R2 upon R of. So 1 by R equivalent equals to 1 by R1, 1 by R2 plus 1 by R3. These are the final expression of resistance in case of parallel combination. Parallel combination, 1 by R equivalent is equals to 1 by R1 plus 1 by R2 plus 1 by R3 when 3 resistors are connected in parallel. So, in parallel combination we discuss current division, how to calculate a current for different path. So, we discuss current division rule in parallel combination. Current division suppose two resistors R1 here, R2, two node M and N, two terminals A dash for R1, B and B dash for A and B connected with node M, A dash and B dash connected with node M. These two resistors connected in parallel are also connected with voltage source and current I is. So, current I1 to R1, current I2 to I2. According to current division rule, current are divided into two parts, I1 and I2. So, total current I divided into two parts, I1 and I2. So, how to calculate I1? First, I1, current flow through I1 is equals to total current I left I1 only R2 total resistance R1 plus R2. Here we calculate I1, so total current is I multiply resistance R2. Resistance R2 when we calculate I1 and divided by total resistance R1 plus R2. Similarly, I2, so here I calculate I2, so we write here I1 divided by total resistance R1 plus R2 when we calculate I2. Here these are the current division. After discussing a current division rule, we discuss star to delta conversion and delta to star conversion. Sorry, the third combination is series parallel combination. Suppose three resistor, one is R1 and two resistor R2 and R3 are connected in a parallel. Resistor R2 and R3 connected in parallel, but these two resistors are connected in series with R1. This combination is called series parallel combination because these are parallel but series with this resistor R1. So, this combination is called series parallel combination. So, 1 by R equivalent is equals to 1 by R2 plus 1 by R. So, R equivalent equals to R2 to R3 divided by R2 plus R3. This R equivalent is total resistance after calculating when R2 and R3 are connected in parallel. So R1 is series with R2 and R3. So R equivalent 1 equals to R1 plus R equivalent. So R1 equals to R2 to R3 upon R2 plus R. These are the final expressions for resistance series parallel combinations. Here we also discuss again some point when this resistor R1 connected into resistor R2 and R3. Here two resistor R2 and R3 also connected in a parallel. These are also a circuit possible. These are the circuit in which R1 is connected with R2 and R3 series, and R2 and R3 are connected in parallel. These are the voltage source and these are the current I. When these sources are connected in a parallel, so R equivalent is equals to R2 plus of R of. So R equivalent equals to R2 dot of R3 divided by R2 plus R of. This combination, this R2 and R3 are connected in series with R1. So R equivalent 1 equals to R1 plus R equal. So R equivalent 1 equals to R1 plus R2 R3 upon R2 plus of R3. These are the final calculation of resistance when series parallel combinations are possible. After calculating total resistance, we calculate a current I. Current I equals to V upon R equivalent 1. So current I equals to V upon R1 plus R2 R3 R2 plus R of. These are the expressions for current that flow through a circuit that are given by question. After discussing series parallel combination, we discuss star to delta star to delta conversion. How to star connected resistor is converted into a delta converted. Suppose there are three resistors R1, R2 and R3 connected in a star, but we want to convert this star connected resistor in delta connection. These are delta conversion R3. This resistor are connected in star, but we convert this star converted resistor into a delta form. There are two terminals, A dash, B dash, C dash. We connect this A and B. We know R12. Connect this B and C. R23. Connect this A and C. R1. So R12 is equals to R1 R2 upon R3 plus R1 plus for R23 R2 R3 upon R3 R2 to R2 R3 on R3 plus R2 plus R of really R31 equals to R31 R1 upon R2 plus R3 plus R4. When resistor are connected is star, but we want to convert this star connected resistor in delta, then we use this final expression. R12 equals to R1 into R2 divided by R3 plus R1 plus R2. R23 equals to R2 into R3 divided by R1 plus R2 plus R3. Similarly, R31 is equal to R3 R1 divided by R2 plus R3 plus R1. These are the star to delta conversion. Finally, today I discuss first what is active element, what is passive element, what is unilateral element, what is bilateral element, what is unidirectional, what is bidirectional element, what is Kirchhoff's law. Here again we discuss source, ideal voltage source, current voltage source, ideal voltage source. We discuss graph. Third point is practical graph in practical voltage source. Again we discuss source, current control current source, current control voltage source, voltage control current source, and voltage control. After discussing the source, we discuss today class combinations of resistor. First we discuss this combination, second we discuss parallel combination, third we discuss series parallel combination, and finally we discuss when resistors are given in a star and we want to convert it in a delta, how to convert star connected resistor in a delta. So after discussing today lecture, we discuss inductor capacitor in next class. So if you like this video, please subscribe, like, subscribe so everyone subscribe this channel. Thank you for watching this video.